Hi, my name is Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. So welcome this Sunday, the 23rd of March 2025, to O-Day. So welcome this Corundum, Conundrum. And I'm listening to myself. I've got a bounce stream there. How is everyone? Let me fix that in the background. Hello, Corky Goss is in the house. So whilst I'm fixing what's going on in the background here, I would like to say that John Hutchison is thankfully at home in home care. He had a small stone, or a stone rather, don't know the size actually, but I presume it's not like a golf ball, hopefully not, in his bladder. And he had had some urinary issues before that, and that had caused him to have a situation, and the scanning came back that that is the cause, and hopefully that can be resolved. So I wish him a speedy recovery. And I had the pleasure of being with Yin Gazda, whose birthday it is today, and she is currently in the chat, so say happy birthday to Yin. Okay, so let me see what's going on here. We'll cut this out over here. And for some reason we've got something going on in the background here. Don't know why that is. Let me see if that's anywhere else. So welcome TK Mills, welcome Claire Westwood, Mela Fury, Martin Kemp, Mika Avila, Venom K, Ken Pratt is in the house. DIY projects with Chauxis, wow. All over the world. Hi, TK Mills. Hi, Ben Polgardy. Hi, John Hoddle29. Samuel Keeley. Is that really you, Samuel Keeley? Hi, Earthworm Jim there. Happy birthday for the other week. Hi, Carmen Miller. Great to have you here. Okay, so let's get on with what we are doing here. Corundum Conundrum. What is corundum? It is aluminium oxide, Al2O3. It's a refractory ceramic, and it is something that Alan Goldwater, no less, rediscovered, that when you heat it over 1,000 degrees centigrade, it actually becomes a conductor. And I later found out that this was the basis for one of the types of Nernst lamps from around the turn of 1900. So what you did in a Nernst lamp, and I saw these physical examples, they were in the museum at Amberley Chalk Pits in Sussex. They had a cylinder of zirconia or aluminium oxide, and they had a heater element around it that would heat it over 1,000 degrees, and then it would become a conductor, and then they would pass the current directly through the refractory ceramic, and this would produce light. And of course, because it is already an oxide, it's not going to oxidize. So this is what we had as one of the options for electric lights before we had the tungsten filament light bulb, which I miss. Ah, the tungsten filament light bulb. And it's also highly stable. Yeah, highly stable compound, and it has a very high melting point of approximately 2072 degrees C. However, we have found that in the lion experiment, it seems to be fluidized. And the lion experiment, well, that shouldn't be going over more than about 1050 degrees centigrade, right in the hottest parts. So how was the alumina becoming fluidized? It wasn't just that. The fused quartz was doing things, and the mullite tube or fused alumina tube in the core was also being manipulated. But let's set that aside. it is a element oxide, aluminium oxide, that has a normally expected melting point of 2072 degrees centigrade. And these elements, aluminium and oxygen, together are one of the principles, if not the second most important rock forming combination in the Earth's crust. And oxygen, often combined with the second most abundant element, silicon, is 46.6% of the Earth's crust. And aluminum is 8.2% of the Earth's crust. So together, these two elements comprise of 54.8% of the crust's mass. Okay? And as I've said before, it is my firm belief that LENR processes over the lifetime of the Earth has contributed a significant proportion of the other elements that are observable in the Earth's crust. And if your main feedstock is oxygen, aluminum, and silicon, then what would that give you? Well, there is always in LENR a call for very simple experiments. And tonight we are going to introduce another experiment that has been developed very recently that may just be a path forward and an introductory experiment for people starting to want to see if the LENR field actually is a real thing. Of course, one experiment that I have spoken about in the past and have recommended to people even in the field of LENR to just see whether it is a real thing is this experiment here by Takaaki Matsumoto. Okay? And what he had was a lead wire, okay, a lead wire, and he had it attached to 110 volts up here, okay, 120 volts rather, in his part of Japan, and he did either 380 millisecond pulses of AC, which is 60 hertz up there, or one 800 millisecond pulse with potassium carbonate or potassium hydroxide in this. And it is a pure lead wire, an absolutely pure lead wire in a pure copper box with this 1 molar or 1.5 molar solution of various electrolytes, potassium hydroxide ideally. And in the case of a potassium, one of these experiments actually, he observed many what he calls products of cold fusion. And the one I chose to put on the front cover here is a lead sphere. Obviously lead is the starting material. And it produced this plume of carbon, which must have come out of here. Now, if anyone knows anything about carbon, technically it shouldn't produce a liquid. It should be either a solid or a gas. And the volume of this material coming out is higher than the internal volume of this sphere. So the implication is, therefore, that this must have been in a coherent matter state or as other atoms, and it was then formed and spewed out of here. What you're looking at here is, from mainstream physics understanding, an absolute impossibility. This is an inconvenient truth. Now, of course, if you were to replicate what Matsumoto had done here, you need pure copper plates. You need pure lead wire. Those are things that are not necessarily easy for the general researcher to get on a whim. You also might need to know your mixing of molar electrolyte solutions to have the potassium hydroxide or potassium carbonate or whatever to hand. And you must be willing to create a circuit and use mains voltages, albeit at the lower 120 volts, to do this experiment. So there's a few barriers to entry in here, and particularly when you're playing with caustic things like potassium hydroxide, that is a very caustic material that can cause damage to the eyes, damage to the skin, the electricity is a risk, obviously handling lead. There's all those kind of risks going on. That means that even for, certain other work environments or school environments, it's a difficult thing despite its simplicity and its incredibly short duration of experimentation. It's a difficult thing potentially for some people to consider doing. So we came up with, and I won't go into it, but you can look into it on the Martin Fleischmann Memorial Project's YouTube at MFMP, a very simple experiment that doesn't have many of these issues. That is, finding specifically pure elements, working with reagents, and working with mains voltages. And that is the Ultra experiment. And so many of you will be familiar with that. You may also, for those that have been following the project, and for those that haven't, I'm going to give you the links just now, that an experiment that I devised a number of years ago, we actually conducted last year. And in that experiment, we were looking to see if what was claimed to be a means of hydrogen production was actually possible in this simple experiment. So we have this $35–40 ultrasonic domestic cleaner. That's the simple thing, but it is a barrier to entry. People have to actually go and buy that. They have to actually go and buy that. We have two very large desiccant pads here to remove water vapor that is produced as much as possible. And we have the whole thing wrapped in a bag. And the idea was to see, did we see her hydrogen production over time? And this experiment was conducted live. And yes, after a period of time, we saw the one peak come up here very, very powerfully. And so, yes, hydrogen was produced. And the theory with this is that the sound energy that's being put in, the 35 watts of sound that's being put in, produces resonant nodes. And at the resonant nodes, you get cavitation. And the cavitation is breaking off the aluminium oxide layer from the aluminium and allowing the bare aluminium to react with the water. Now, you'll see later on that the reaction producing hydrogen actually starts at 25 degrees. But as the temperature increases, it increases the speed of that reaction kinetics. And so, of course, the reaction itself increases the temperature. So there's a positive feedback loop there. The aluminium with water producing hydrogen and aluminium hydroxide, that actually produces heat, which accelerates the process. Now, what I'm interested in is our work had identified that H2 is not active in the fractal toroidal moment, these electrodynamic structures that appear to do transmutation of elements in their pseudo-magnetic monopole cores. But H- and a proton and so forth, they have a magnetic moment. And so the exact place at which you are producing this atomic hydrogen and protons from this reaction is the place where you require it to be fed into these little micro machines that are being produced at the transverse of the standing waves of the ultrasound in the water impacting the aluminium foil. But of course, we didn't want to stop there, because in the past, I'm calling him Doctor, but he deserves it. My good friend and colleague, Alan Goldwater, he had conducted an experiment like this, and on a hunch, an educated hunch, we expected to see the formation of iron-rich crenellated microspheres. He ran a test in this particular device that you see here on the screen a number of years ago, and he ran it for 900 seconds with an some aluminium foil in there, and he produced these iron-rich crenellated spheres and a broken section from one, and we analyzed those. And on the outside, it had silicon dioxide. So you had the iron oxide, of the iron-rich crenellated spheres. And outside of that, you had silicon dioxide. And on the inside, and partially on the outside, if you remember, there was magnesium. Perhaps I can pull up an image of that analysis so that that is clear for you. If I have it here to hand, I might do. If I don't, then I won't. Let's see. Where are we? Here. Okay. Right. So, in this particular image, you can see one of the Allen Goldwater iron-rich crenellated spheres. And on the outside, you see this deposit. And it turns out that that deposit is silicon dioxide. And in this inner section of a broken one, you can see in most of the spots, 4 out of 7 spots, there we have both silicon and magnesium. Okay, both silicon and magnesium. No aluminium, interestingly, but we have iron, silicon, and magnesium. Now, with respect to similar phenomena to Matsumoto here, we have experiments, for instance, by Henk Uren, where we get the same kind of iron-rich crenellated spheres, but spewing out of it, here, this iron-rich crenellated sphere, spewing out of it, out of the top pole, we have this deposit here. And what is that? That is carbon predominantly, just like Matsumoto saw, and oxygen can be from anywhere else in the system. Moreover, when we look at the disks coming out, we see, again, carbon, and this is out of the pole, coming out of the pole, just like it's doing, only one pole, by the way, just like it's doing on Matsumoto's work. We also see 21% by weight of titanium, which is the fusion of CO2. Okay? So, very, very interesting finding there. Similar kind of things going on in Malcolm Bendel's system. Of course, it's open to the air, it's using hydrocarbons, so you're going to definitely see carbon in there. But same kind of structure witnessed there. And also in Binzhuan Huang's reactors. And again, in Binzhuan Huang, we have the iron-rich crenellated sphere with these toroidal bits inside. I wasn't able to look at the elements in there because the EDS wasn't working on this time, but we put it on another experiment and we saw these toroidal clusters inside a broken one of these structures with the iron oxygen on the outside, and inside there the element was in fact titanium predominantly, and carbon and oxygen. And again, the fusion of CO2 goes to titanium. You can also see a little bit of aluminium in there. Okay, so that's a little bit of background of some of the things that have happened in the past. And so I want to return to the presentation of the day, which is the Ultra experiment. And in the Ultra experiment, like I say, I took some of the aluminium foil out of there. I selected one of the pieces in there and I looked at it, and there was a very large mark. So you can see this is 40 microns across here. So the center part of this interaction spot here is at least 40 microns, okay? And it has a hexagon arrangement much further out, and then it's unaffected aluminium at a further distance, okay? So I believe that this was probably the sort of cluster that might lead to the formation of an iron-rich crenellated microsphere. But if we look at the elements that are being synthesized here, and I will go into a close-up of that, we can see that over this area here, and I actually did a line scan in here. If you go the line scan, it's very different elements over here compared to this central ridge spot and the cavity in the middle. But what we see is, again, iron in every case of these spots, and then we have silicon, aluminium, and magnesium. Silicon, aluminium, and magnesium, and of course carbon and oxygen. Okay, now obviously in a ultra experiment we're going to have oxygen in the water. Okay, however, could some of that oxygen be coming in a different way? Don't know, but I expect the oxygen's coming from the water. Also, you start with aluminium oxide layer on the surface. Okay, so the argument is therefore that, and I've made this many times before, and this is based on George Osawa's original work that was validated by Sundaresan and Bokros in the middle of the 1990s. Sundaresan on secondment from the Babratomic Research Centre, and also John Bokros, one of the world's greatest electrochemists at Texas A&M. They found the production of iron only when they had oxygenated water in using carbon electrodes and arcs. So they had carbon electrodes and arc between them, and when they had oxygenated water, they saw the synthesis of iron. And I argue that the fusion of carbon and oxygen is silicon, and an exchange reaction of carbon and oxygen produces aluminium plus hydrogen. And when you start interacting, thank you very much, Vanilla Isis, for that $10, very much appreciated. When you start reacting aluminium with itself, you'll see in a minute that it actually does exchange reactions and produces silicon and magnesium. And when you have aluminium and silicon in play, you'll see what that does. Okay, so very clear peaks here, silicon and magnesium. And when you do a line scan across here, maybe I can go back to the video here. Is it going to let me do it? No. Yeah. Not this one. No, it's not going to do it. And that's the hydrogen experiment. Anyway, when I do a line scan, you can go and look at it on YouTube. You can see the magnesium and silicon are coincident on these ridges. Okay, so I believe the aluminium is doing something, and this is what I think it might be doing, that you're getting an exchange reaction, and you can go to the MFMP's low energy nuclear reactions calculator at nanosoft.co.nz that was built around Dr. Alexander Parkhomov, his birthday recently, and his 80th birthday recently, and it was his calculations that myself and Philip Power built into this calculator. This is free to use, 2to2.php for exchange reactions, and you say, I'm going to put aluminium in and aluminium in to the two elements on the left-hand side of the reaction, and let's see what produces silicon out. In fact, most of the reactions in this case are silicon in E4. And what do we get? Aluminium plus aluminium produces magnesium 24 and silicon 30, or magnesium 26 and silicon 28, or magnesium 25 and silicon 29. And so the idea that in this ultrasound experiment and the ones that I was showing with the work of Alan Goldwater, we would see potentially the formation of silicon and magnesium from an aluminium foil. Then these are the reactions, and these are not massive energies, but 3.9719 is nearly a million times more energy for a particular reaction than you get, for instance, it's of the order of a million times more energy than you get from even hydrogen making H2. So when you've actually therefore got aluminium and silicon in play, and you go and look at fusion reactions, what do you get? Well, aluminium and aluminium gives you iron 54, just a straight fusion reaction here, and 21.8426 million electron volts. This is approaching deuterium fusion levels of energy for a reaction. Okay? Aluminium 27, silicon 29. That is iron 56, the most abundant isotope of iron. gain 21.51 million electron volts. Aluminium and silicon 30, iron 57, the rare isotope, the spin isotope of iron, 18 million electron volts. And then when you get to silicon 29 and silicon 29, you produce nickel 58, which is the most abundant nickel isotope, 16.431, and so forth down the list. But of course, if you're using your 29 here, and you're more likely with abundance of aluminium to be producing the most abundant iron at this point. So what we are seeing in these reactions, potentially, with iron potentially being produced in these areas. Thank you very much, Winone Riders, for that $20. Am I familiar with Donald E. Scott EE? I feel like his work on plasma cosmology is very relevant and intuitive to the work of Birkeland currents, reverse coaxial movements and distance. Layman interests in your take. I think, yes, I think there's a lot of that going on. I think he's something to do with the electric universe, if I'm right in saying. Yeah, I think he was on the money. Okay, so that's very kind of you. Very, very helpful. So what we observe in multiple experiments in ultrasound appears to be and in plasma experiments and in other experiments that we've done, but ultra has been very well described, is the production of the precursors from aluminium to make iron and extraordinary levels of nuclear level energy here for the pathway to producing iron. Thank you very much, Black Tie, for that £10. Very much appreciated. So this is potentially a huge amount of energy. And this got me thinking. This got me thinking about what Anatoly Klimov said in his presentation in his process of celebrating the work of and life of Alexander Parkhomov. And he made a case here that the strategic security of the Russian Federation in new energy technologies and the relevance of the new scientific and technical direction of hydrogen metal energy, Lena. And he's arguing that the reason that the military in the West are focusing on supporting hydrogen metal energy processes is that it is for dual use. This should say hydrogen metal energy as well. It is reported that onboard generators of heat and electricity, as well as high energy substances, have been created, blah, blah, blah. Creation of new energy saturated explosives, EE, and rocket propellants with high energy content based on hydrogen metal energy, LENA technologies for modern aircraft and sea torpedoes. And he also talks later on about missiles. And he quotes this missile, which was done by Purdue University and Pennsylvania State University. And this uses a rocket propellant called Alice. And what that is water ice and aluminium nanoclusters. Okay? So I thought I would do a little bit of homework and see if his claims could be verified. So firstly, I wanted to see if this aluminium nanoclusters plus water could actually produce a propellant. Now, we know for a fact that normally passivated, that's when you already have aluminium oxidized, it is very resistant. As I said at the beginning, this material, aluminium oxide, corundum, is very chemically resistant. It's very stable, and it protects the bare aluminium underneath. But if we have raw aluminium, pure aluminium, with no oxide layer, then it'll start to react at 25 degrees centigrade. But if it's frozen into water ice, the likelihood of the reaction occurring while the water remains in a solid state is extremely low. That is to say, it basically won't happen. So if you'll just forgive me, I lost something here. Okay. Just lost my switcher. So essentially, if you have bare aluminium in even normal water, the Gibbs free energy of that leads to a reaction which produces hydrogen. So I actually should have another bullet point in there, and that's what I'm trying to correct, and I made a mess of that, didn't I? So in the first instance, there's basically no reaction with straight pure aluminium in water. We know that in our Ultra experiment conducted last year, that when you clean off that aluminium oxide layer, you start producing hydrogen even at room temperature. Okay? When you go above 100 degrees centigrade, so like you're already starting to boil that, and I believe we got to around about boiling temperature, if not very close in our experiment last year, and the aluminium is exposed to this higher temperatures, and imagine if it's already practically at 100 degrees, it's going to be at 100 degrees at these reaction sites. The increased thermal energy and gaseous water, it greatly enhances the reaction kinetics. Okay? So, this is actually what we physically observed. As the temperature went from room temperature and raised it, the production of hydrogen went up. This was live demonstrated last year in an Ultra experiment. And actually, the US military have looked at this in the past for hydrogen production in the field. Now, the next slide, which I think is critical that I just want to go over before we go into this new potential approach. He was saying that in his view, LENR reactors and a heterogeneous mixture can be used as fuel. He's suggesting rather than using metal nanoclusters that you can even use cheap carbon nanoclusters. Now, what would that be? Cheap carbon nanoclusters, well, that might be exactly what there is in a thunderstorm generator. Carbon nanoclusters, unburnt carbon. Why wouldn't it be? And then, because you have done thermocatalytically splitting of the water, you've got extra hydrogen in there. That's my argument right from the beginning, before I'd even seen an operating unit. Then when you've got magnetohydrodynamic multi-axis shear with cheap carbon nanoclusters, which is unburnt carbon from the hydrocarbon, and hydrogen ions coming from the thermocatalytically split water, going into the one stage of the thunderstorm generator, the catalytic process above 650 degrees of thermocatalytically splitting the water, producing oxygen, hydrogen. Any unburnt carbon might form carbon nanoclusters. We certainly see things that look like nanoclusters all over the inside of the 500-hour run reactor. Then could you have these processes going on? I don't know, but this is what Klimov suggested, and that is where they're going. Don't need to get some fancy metals, don't need palladium, don't need platinum, don't even need aluminium. We're just going to go even with cheap carbon. But ballpark, even when he was using aluminium and other materials, the typical COP reactors from his multi-axis hydrodynamic shear plasma vortex reactors was typically, without a secondary material to receive the neutral clusters, reached between 2 and up to 4, a COP of 2 and 4. And he argues here that currently detonation modes of such mixture have been obtained and studied. The energy release in the indicated mode, that is, nanoclusters, which could be carbon, but nanoclusters in the case of Alice of aluminium, and hydrogen ions, okay? And I will explain where the hydrogen's coming from. It's coming from the aluminium nanoclusters producing hydrogen from the water. So you've got, by getting the mix right of nanoclusters of aluminium and the nanoclusters and the water and getting that whole mix right, you'll end up with the right stoichiometry to produce the desirable effect. He's suggesting you're getting something that is a COP, that is extra energy of between 2 and 4. And that is a non-chemical energy, okay? And that this can lead to typical values of detonation release that exceed TNT by 4 to 10 times. By 4 to 10 times, okay? Transmutation of chemical elements was detected and studied in such plasma vortex reactors using optical spectroscopy and EDS spectroscopy. So I was showing you earlier EDS spectroscopy in an ultra experiment. Optical spectroscopy is when you have a little optical fiber looking at the photons coming out and you can see spectra of atoms that were not in the original material. And this is a more real-time process to observe the elemental transmutations going on. So I thought I'd do a bit of homework here and look at the energy calculation compared to TNT. So in our Alice propellant, in that missile, you have step 1 is the initial reaction, which is the reaction of aluminum. I've actually put aluminum there with water. And then step 2 of the reaction is the combustion of hydrogen. And the hydrogen then burns with oxygen from the air. So you've got an additional component of your fuel here. Now, in the case of TNT, all of the fuel for the detonation is within the trinitrotoluene. It's all in that chemical. So it burns and it doesn't require extra oxygen from the outside. What I'm proposing for a fuel propellant here in the air is that you're getting energy from the initial reaction, but you're also getting energy from the reaction. Thank you very much, Bob Wildfish. That is very, very generous. $99. Very generous. Thank you for inspiring me to study this topic. I sincerely appreciate you making all the info public. Being 100% public is the only way for this to get out. Absolutely full on. I totally agree. Thank you very much for that kind donation. So, what we're looking at here is that the reactants are 2 aluminium atoms plus 6 water molecules plus 3 H2O plus 3 halves of oxygen from the air leads to 2 aluminium hydroxides, 3 hydrogens and 3 H2Os. And yeah, you essentially will burn the hydrogen in the air. Okay. Now TNT here has a energy content per kilogram of 4.184 megajoules. 4.184 megajoules. Aluminium plus water reaction plus oxygen from the air in total, including the weight of the water, the weight of the aluminium and the weight of the oxygen, comes out at 10.46 megajoules per kilogram. That is 2.5 times the energy content per kilo than TNT. Okay? And then what I've done here is I did this calculations with Grok, so you can go and verify my discussion and calculations. This is something that Grok does very well. Okay, so you can go and use this link and you can see my entire workings here. But 2.5 times is definitely not 4 to 10 times. It's definitely not to 4 to 10 times. However, he did say that this, because there's transmutation going on, and we see transmutation in our ultra experiments, and I've shown you that if a small amount of that transmutation goes on, a phenomenal amount of energy is released. A phenomenal amount of energy is released. How much energy? Well, in aluminium to aluminium reactions, which may be part of the equation, you are getting 1,000,000 times more per reaction in an exchange reaction than you are getting from hydrogen-hydrogen recombination. And in the nuclear reactions that are not exchange reactions but are fusion reactions to iron, which is the product that we see in multiple replicatable experiments, we are getting nearly deuteron per nucleon, not per nucleon, but per reaction levels of energy. Okay, so if a small fraction, and could you imagine that in this rocket nozzle, there is a lot of multi-axis hydrodynamic shear of these reactants? Could you imagine that some portion of this environment has the required dynamics, the required kinetics, the required turbulence to lead to our fractal toroidal moment structures that force the production of the phase singularities and the topological monopoles to do the nuclear reactions? Do you think it's possible in this extreme turbulence going on here to produce a small amount, a fraction amount, as we're observing in the turbulent plasma vortex reactors of Anatoly and Klimov? Do you think that some proportion of that is able to produce low-energy nuclear reactions? I think that may be going on. And if that's the case, when you combine the 2.5 times with the COP of 2, you get around about 5. And when you combine the 2.5 times with the COP of 4 here, you get around about 10 times the value of TNT. But of course, this particular material relies on the plasma vortex magnetohydrodynamics, multi-axis hydrodynamic shear that would be going on in the rocket here. Firstly, the material is not going to detonate. You don't want the fuel in your Alice rocket to detonate. You want it to burn. You want it to burn. And we know that as long as you keep your fuel frozen, then it is the aluminium nanopowder is not going to react with the water. But as soon as you start hitting that with an initiation plasma, thank you very much, Bob Wildfish, for that $20. How do you deal with the knowledge that this tech could be used by bad people to make very bad things? Nuclear proliferation is a big challenge, and this potentially much easier and more destructive once mastered. This process is, you still have to have a fairly high infrastructure, and the type of reactors that I think you will produce are practically going to destroy their containment, and they will only keep operating as long as they are on. As soon as you turn them off, you won't be able to switch them on again. Okay? So these are one time on, keep them running, and then, you know, replace the core. That's what you would have to do because of the way this works. Because of this way this works. The bad guys have already got this, and I argued this with Ashton Forbes a couple of weeks ago. I had to make a decision in 2017. How do you move forward knowing that this has already been weaponized? Well, if you always believe that the next ruler or autocrat or even democratic organization running a country, because sometimes it's difficult to tell whether something's democratic or not, can you always guarantee that the people that have access to this working versions of these technology aren't going to blow up everyone anyway? This isn't mostly an explosive technology. What I'm arguing here is I'm supporting Klimov's claims that there's a combination of a extreme chemical reaction that can also produce access to nuclear level energies, and the combination of the two makes a better propellant. So if you've got 10 times the propulsive capability of your propellant, you can have 10 times less mass to do the same work. So, you know, could we all be running around in aircraft that actually are run on frozen aluminium nanopowder and water propellant? What is the product that will come out of that? Well, aluminium hydroxide and water. I mean, but if it's 10 times more energy, then, and in theory, some magnesium, some silicon, and also some iron crenellated microspheres. But if that's the case, then we could have aircraft that have much, much, much less fuel on board to do the same work. That just alone is something to consider. So from my point of view, I look at this as, what can we do positively with this? Because the bad stuff is always a potential to happen with the people that already have it. Okay? And I don't want to see humanity suppressed. So there is nuclear level energy. There is nuclear level energy, in my view, in various experiments. We have seen the process do what is necessary. And so I think that the combination of outcomes here leads to the purely chemical reaction here by kilogram being 2.5 times TNT. And the fact that we have multi-axis hydrodynamic shear going in here, turbulence will lead to the fractal toroidal clusters of the charge-separated material, which will have the topological monopole, which has the phase singularity, which has the Aharonov bomb effect, which can cause this intense magnetic pressures and coherence of matter that lead to nuclear exchange and nuclear fusion reactions, which then lead to a COP that is over a chemical potential reaction of 2 to 4, readily, easily achievable in vortex plasmas. And that leads to a verification, in my view, of the claims of Anatoly Klimov. And this kind of thing, where you have some transmutation products coming out of the reaction core here, or as I have showed in the past, you can have in other experiments, for instance, to pick one from the top of the tree, this one here, where we have in the phase singularity, which is here at the top of the tornado of the overall magnetohydrodynamic structure, we have a iron-rich crenellated sphere, which has come from here and it's come over here and it's spilling its guts from its core top here. There's all this material spewing out, and I believe that that's what caused this to launch over here. And from the subtor that was here, there's a subcore here. And you can see how it has this trail behind it, This is what we often see. Moreover, over here, there's in my view, an N-1 core attached to this larger ball here. This is exactly the same size as this core. And so I believe that it's almost like a little moon orbiting a planet Earth over here. Here's another one. Again, iron-rich crenellated core in this broken up structure. You've got carbon and magnesium and sulfur and so on, but you have also silicon dioxide on the next bit out. Silicon dioxide on the next bit out. Okay? So, are there any questions at this time? This was the structured part of the presentation, and I'm going to move on to an interesting couple of pieces of data, which is much less structured, but I think it's incredibly important to share this at this time. So if you ask some questions, I'm just going to throw a couple of slides together here, or I'll go to the resource directory maybe. Okay. So there is a guy that has been conducting experiments. He's an electrical engineer. I don't know where he's from. He wants to remain anonymous for quite good reasons, many of which I could recommend. And he has been publishing his work on Lena Forum. He's been interacting with me over the period. And as of last week, he did something that really deserves to be shared, because it possibly is a new introductory way that people can get involved with this process. And in his instance, he's reduced it down, I believe, to something that is even more laughably trivial than the Ultra experiment, but at its core is the same process, potentially. Certainly the evidence is moving in that direction. Okay, so the first video that he put on, or rather data that he did online, was on February the 11th, 2025, and he was conducting a whole bunch of experiments here. Thank you very much, Win On Riders, for that $5 donation. You're saying, I think the answer mathematically is in plasma torus being spun and knotted in one direction within a sphere of mirrors resonance to make artifacts. Perhaps. Certainly there are many plasmatori involved in plasmoids. Okay, so he says here, as he starts commenting, it so happened that I've been feeding into a small neural network the work of George Eagley, Bob Greenyer, and Lutz Yetner, with many of the publications they refer to, with an intention to come up with suggestions for simple experiments to explore EVOs, condensed plasmoids, fractal toroids, etc. Anyway, so he is an electrical engineer, and he has produced these spark discharges using a high voltage sparker. You can go and explore what he's put in here. He's sharing the scope outputs and some of the marks that have been produced by these various things. Okay, and it's a nice exploration of his work. I don't know. This is water spark plug. Here's some marks that he's showing where you have the initial spark and some things going on around the outside. Okay. And he's looking at this work by Bogdanovich of the long-lived plasmoids, living for about 2 days after the experiments. There was additional presentations by Nestorovich that he actually alerted to me, and I spoke about those. So thank you for that, Tibi. And so this is how someone with a willingness to explore this space can actually go ahead and make a real breakthrough. And potentially what he's done is a real breakthrough. So below is a simple sample of aluminium. I've now tried long exposure photography with makeshift ND filters to capture the plasma of one or several discharges and high frame per second video. By the way, I have no idea on the alloys that I'm using. They're just scrap pieces. So scrap pieces can include silicon and aluminium. However, whatever, it may also include iron. Okay, fine. It's just the way all of these things come together into these clusters that I find is interesting. And moreover, and further, that they are hollow, and even further than that, that you can have toroidal structures going into them and synthesizing new elements and them spewing out in a volume that is higher than the internal volume of the structure of the sphere. Anyway, so here's some of his experiments here, and you can see it's quite a involved setup. So you can see he's got some chops here. He's got a capacitor bank here. He's got an electrode here, and the aluminium, and so forth. And he's got some arcing going on here that he's caught with high voltage. Okay, now I'm not so keen on these particular experiments from the point of view that they are a fairly big barrier to entry. You need to understand how to make a fairly high-powered spark discharge system and so forth. But as you will see, I think he's done a wonderful job when it comes to the end of it. So so he goes on, he goes on, he goes on. Like I say, it's all available, and I will share the link in the blog afterwards. He's got even more experiments going on here with some coronas going on, which we know also produce transmutations. And he's starting to observe these separate objects moving out from the main structure here. And he's also observing like particles coming off, sort of thing you would see and basically dismiss in spark discharges. Now, the interesting part here is that he has a rolling shutter on his high-speed camera, and it's partially exposing in the initial flash of the discharge part of the frame as the scan line of the rolling shutter is coming down. This is not something that's magic, it's just an artifact. Also, this glow ring will probably have been all the way round, but again, the rolling shutter is only picking up part of it. Okay? And this is why you really need global shutter, fast frame rate cameras to be able to do accurate videography. He's seen things flowing around in non-kinetic paths, and he started to see these kind of effects in later experiments. So he then started putting water, deionized water, and aluminium foil on top of the thick aluminium plate and trying discharges, and he ended up with these kind of structures, which I think are really rather fascinating. They're like localized bubbles, and some of the bubbles have holes cut into them. And this starts to look to me to be really rather exciting. Obviously, some of the dynamics, again with the rolling shutter causing this issue here, can look quite spectacular. Sparks flying everywhere. And some... Now, this is where he changed from something that's a little bit difficult to set up for the average Joe to something that is very, very simple. And I believe possibly is a simpler experiment to create one of the core effects of this process. And essentially, maybe I can download that thing here. And we can have a look at it. Give me a second. Thank you, Bob Wildfish, for that $4.99. I agree, Uncle Sam already has weapons built this way. Do you lose sleep over terrorists being able to make Coulomb bombs? They've got knives, they've got guns, they've got a lot of huge amounts of weapons. If someone really wants to kill you, they're going to find a way to do it. And who's to say they haven't already worked it out? You know, some of these so-called terrorist organizations, they have some very capable people working for them. Not that I know anyone personally, but I'm saying the assumption to say that you have to feed it to them, spoon feed it to them, you know, I think they probably know. So this is using the same setup at this point. But this is where he has the aluminium plate below and the aluminium foil with the deionized water in between. And you can see the slow motion on the sparks here. Again, it's the rolling shutter that you're seeing going across. But you can see the sparks coming off. Now, you note that the electrode is here, but the sparking occurred over here at this point. And he does another one here in a second. Right, so the sparking occurred over here. So the discharge path is not necessarily in the place you would expect it. When on radars, so is the ether real? I'm a layman but think so. Yes, I believe it's real. I absolutely believe it's real. Thank you for your donation. Okay, so this goes through a whole bunch of explosions, and you can see there's more action going on over here. Okay, you get the idea. Right. So, then I had some conversations with him, and he starts saying, hunt for iron-rich crenellated microspheres. How would one do that? Wrap a neodymium magnet with a white plastic film, place it close to the target, and scrape a bit of the target with plastic spatula, see if the magnet catches something? Question mark. He's obviously... he's been watching, let's put it that way. Also, on the investigation side, do we have friends who have a phantom, or at least... So he's looking for high frequency, but here he's got some view on the top here of the process. Let's look at that a bit bigger. So this is a GIF, and he's produced some really nice GIFs of the process at play. So you can see when one spark occurs, it actually occurs in a large area. And there's a lot of excitement going on, and it kind of spreads out. And do you know what he's done this with? A capacitor. That's it. A capacitor. I'm going to zoom into this area here. So he's got the negative of the capacitor here. And the explosion starts here and it spreads out. Watch it again. Absolutely awesome. A big round of applause for Tibi and for his courage to do this work and share it openly. Okay, then it gets more interesting because he has a full DIY guide here. Right, so I think this is it, maybe. He actually produced a whole GIF animation, which is a DIY guide. So, multiple discharge events in groups in random locations. That's the kind of output you get. Okay, so underneath the plate pair through... with light on. So light off, light on. So you can see underneath you've got two sheets of aluminium, top side of bottom plate only through light on. So you can see there's big holes, but there's also these explosions going on. These are the many micro discharge events. So you have the initial discharge event and then plasmoids going out, plasmatoroids going out and doing more reactions. So using a pipette and distilled water, about $2 for quite a lot of litres, from your local shop, you put a smaller piece of aluminium foil with the edges bent up. The reason you bend up the edges is to prevent focusing of the concentration of the charge. Okay, so the smaller bit, which will be the cathode, is on top of the other piece of aluminium foil. Then you take a capacitor, this is 4,700 microfarads, and you charge it to, say, 35 volts. And then, boom, an event going on over here, and some here, and some here. This is absolutely absurdly simple. Absurdly simple. So, what are the implications of this? The implications of this, that you can do this experiment that I'm showing you on the screen here. Yeah, there. I can get it right. There. That Tibi has done. You can do this experiment. And look how these are in a regular array here. Wow. I'd expect maybe there's an iron-rich crenellated sphere in the middle of each of those circles. There's a lot of blue ocean here to do, right? Lots of blue ocean of experimentation. But this experiment potentially can be done for almost zero cost. What do I mean? You probably have some old electronics lying around in your house. It's very likely in those old electronics you can find a capacitor of about 40 volts of about 4,700 microfarads. Electrolytic capacitor. You probably can find that. If you can't, it's going to be at your local scrap electronics at your municipal dump. There's no reason to be paying even probably the few cents that are required to buy that capacitor. 1. 2, he used a lab power supply, a 40 volt lab power supply. You don't need to buy that. You could just buy, say, 4 9 volt PP3 batteries. Okay, 36 volts. That's sufficient to charge that capacitor. But here's the thing. You don't even need to buy that. Normally, at your municipal dump, they will have a toxic battery waste area. Or in your DIY center, they'll have a battery place to put batteries, right? It is often the case that old PP3 batteries, they won't run your smoke alarm. They won't run this or that. They just don't have the ability to drive the current. But they do have the ability to provide the voltage. So even old second-hand 9 volt batteries gang together, it will be able to provide the voltage necessary to charge a capacitor. Then you need aluminium foil. The last component that you need, that you might actually have to spend some money for maybe as much as a few dollars, is your distilled water. That's it. That is it, my friends. We are talking, we've moved from lunchtime money to do many ultra experiments, lunchtime money to do many ultra experiments, to the cost of not even able to, well, I guess you could buy a decent cafe, an espresso. With the cost of an espresso, we are now talking espresso cost experimentation. I was amazed that I did not have a single report from the $11.7 million, euros rather, that was spent in the Clean HME fund across Europe. 11.7, no one spent $35 or $40, to the best of my knowledge, within that program of 11.7 million euros during the 5.5 years, 6 years that it ran, to actually do an ultra experiment. You have to order something on Amazon. It might take you 20 minutes. It takes you about 7 minutes to do the experiment. It probably takes you longer to unwrap the ultra equipment than it does to actually prepare and run the experiment. You have to buy a cake tin. But there is zero excuse for not being able to do this experiment. Now, I'm only going on what Tibi has shown, but what I'm about to show you is very, very interesting. Because Tibi managed to get a friend, wherever he is, I don't know where he is, and do an analysis based on what he did. So what he did is he actually prepared around about 12 of these pairs. He did multiple sparks until essentially the whole surface was those kind of little pits. If they welded together, then he peeled them apart and put them down again and gave it a few more shots. And then he used a fresh, clean toothbrush to brush both sides of the foils to extract potentially any iron-rich crenellated spheres. And then he used a fairly standard technique to extract magnetic structures from them. Okay. Well, we go here. So he's got all these different images here. You can see a whole bunch of them with the effects on there. Now, this isn't from this particular experiment. This is from another experiment because he originally had, you can see in this experiment up here, he's using the actual leads from the capacitor. And the leads from the capacitor, unfortunately, these leads from the capacitor are ferromagnetic. So unfortunately, you kind of basically got to write off any iron-rich crenellated spheres you might get from that because you've actually started with a ferromagnetic material. That will be contamination. However, from these set of initial experiments with the capacitor, he actually found that when he placed the spheres that he'd gathered with a magnet on some paper, and the paper has a magnet below it, then he could push them around and they're aligned into bead strings. Okay, this is not magnetized in that it's permanently magnetized, although it might be, but in this video the white paper is sitting on a magnet, so don't read this wrong. I did initially read this wrong, but I clarified it with him, and there's a 2.5 hour interview with him, not with his visual, but where I discuss these series of experiments with him and the way forward. So that will be published tomorrow. Okay. So yes, in his case, what I did, and I did many things wrong, using an old potentially contaminated toothbrush used for cleaning, he scraped with the brush onto fluffy toilet paper 6 aluminium foil pairs and freshly prepared almost each. I did a 4700 microfarad 35 volt capacitor with the original capacitor leads that are magnetic. Found out late, charged to 24 volts until I got many craters using a neodymium magnet and so on. So that's how he got that. It's all explained there. Okay, and he's got a video to download that video in a better quality. Now, he went on to say that the pits that he saw are similar to those observed and shared by one Ken Shoulders. Okay, so he's saying that he thinks these pits, and I would agree with him. They kind of basically are. Okay. And he's also talking about, look at the splatter that you have here in Ken Shoulders' work. And here the splatter that he has in his experiments. Okay. Similar kind of effects going on. And I would agree. Okay. And here, when you look at this up close, look at these conical pinches all the way over here. I would argue that this is where the action is occurring. Okay. So he says, the good news is I remade both low voltage and high voltage experiments, being very careful to avoid ferromagnetic materials and contamination, and still ended up with the ferromagnetic microspherules. I also have a good chance to receive geometry analysis with an SEM thanks to a local friend. Are you ready? The bad news is no EDX capability. Oh. And SEM activity to start no sooner than... Oh. Okay. All right. This was on March the 1st. Okay. And so he's asked Alan Goldwater. I've spoken with Alan. Alan has the capability to replicate this with SEM and EDX and verify what you're about to see. He's also showing here how in various experiments, and there's several other experiments where these things occur, where there are not just kinetic movements, there are things that are move in what are not normal kind of directions. They're like, here, for instance, this one here, that's not a kinetic movement. This particular particle here, if I zoom in and it runs again, moves down this way, and then it kind of changes direction. And I've actually seen these in videos of that I've analysed of HHO, a Mars gas, interacting with various materials. Okay, so this is like a little ball lightning structure. So he's done his homework here. He's done his homework. Thank you, Scoggy Hoggins. Very much appreciated. He says, Bob, if you were to machine aluminium caps to fit over the leads, would you consider then this experiment to be contaminant free? No, so what he's done is he charges on the iron leads, but connected to the iron leads, he has physically soldered copper leads, and he repeated the experiment with copper leads. Okay, so there's no ferromagnetic materials in there. Okay, and we're going to come and see what the output of that was. So this has already been done. Okay, again, he's looking at this particular trace over here where a particle does something that's a little bit more interesting than going in a particular direction. Okay, so he's making a suggestion here about how this changes direction. I think in this particular instance, the one that he highlights, it could have hit the surface, which you don't see. Now, this becomes very interesting. You ready? Are you ready? 3, 2, 1. Boom! This is what he found. Can you see it? And it's about 22 microns across, so it's the normal sort of size for non-resonant or basic structures here. This is what he found. Now, he actually has several different ones highlighted here. These are from high voltage experiments. High voltage experiment, high voltage experiment. This is the carbon tape on the SEM, and this bit here, this grouping is from the low voltage experiment here. And you can see here in the optical image. And so the optical image is rotated. This is the low voltage group. So this was done with copper leads with a 4,700 microfarad capacitor recovered from an old electronic device and charged to 35 volts. That would work. And so you can see it's the same grouping. So you've got two big ones, an even bigger one, and this one, and a couple down here. And so it's just rotated. Two big ones, an even bigger one, another one, and a couple down here. Okay? So that's the one he's looking at. And are you ready for it? Are you ready for it? 3, 2, 1, boom! This, my friends, is awesome to me. Because he not only has the iron-rich crenellated spheres, but he also has what I would say, and when this is looked at with EDS, I would say this would be the FeO plus, the FeO plus O, Fe plus O, and this would be silicon dioxide spheres. And these are roughly the same size in each case, and these are attached to the larger structure, and this looks remarkably like what I showed you earlier from the Henk urine exploding ball lightning structure, which I showed you here. This one. The iron-rich crenellated sphere with the N-1 core proximate to it. And here is an N-1 core. And typically you can see this N-1 core is totally smooth, and that indicates to me that this is mostly silicon dioxide. Okay, this glassy substance here could be, and most likely is, silicon dioxide. So it could be at least covered in silicon dioxide. And what you are looking at here looks almost exactly the same. Almost exactly the same as the original 2016 Dusty Plasma Fusion George Eagley reactor products that we produced in about an hour outside Budapest in Hungary in 2016. And it was the first time that I saw iron-rich crenellated microspheres back in 2016, nearly 9 years ago. How far have we come? A very complicated Dusty Fusion plasma reactor, and then you get this kind of action going on. Now, you can, someone says, when are they getting a home SEM? Well, that's difficult, but here you can see that, you know, even with an optical microscope, you are able to observe the action going on here. You can see the spheres, okay, even with a optical microscope. But for me, this is a huge boom because you've got 3 spheres that are roughly the same, and another bunch of spheres that are roughly the same magnitude. Okay, I think this is going to be ridiculously easy to replicate. Here's the one on the left. This one here, close up with a bit better resolution. Clearly, the same kind of thing. These structures are normally 1 micron across. Normally 1 micron across. That's 5 microns, so that is around the right scale. And these are from some of the other areas, which are from high voltage. And the high voltage, I don't think will produce necessarily as good ones. These are from different processes, and we're going to look at that in a minute. Okay. So, I want to thank Tibi for his contribution here, for sharing his work. And this is absolutely fantastic because essentially for almost zero cost, this is, you know, I used to say to my colleagues, we're at this was when back in 2019, we're at the point now where if you think your PhDs are worth more than soiled toilet paper, you know, you should at least try to see for yourself whether this is what's happening. And whilst the iron-rich crenellated spheres can be produced by micrometeorites, they can be produced in other processes. I believe all of them rely on plasma, possibly and quite likely hydrogen in play, or at least water, hydrodynamic shear, and so forth. Skoggy Hoggins says, thank you for the £5. Bob, could they verify it is iron instead of somehow ferromagnetic reacting aluminium alloys? No, those particular morphology that I'm showing you here, I've seen so many of them that this is definitely iron and oxygen. Definitely. This is definitely iron and oxygen. This is what it looks like. Nothing else looks like this. It's this iron and oxygen. Okay? And from experience, when this is replicated, or even when they take this particular SEM stub and put it on an SEM that has EDS, I'm pretty certain that you will find out that this is silicon dioxide. This is silicon dioxide. If I will go to the original ultra. I should go to the original analysis of the Nova reactor. Let me have a look at that. Give me a second. Here we go here. to go back a long way. Forgive me, it was in 2017, not 16. So, okay. So you're seeing here, these are the iron-rich crenellated spheres, bearing in mind that the inside of the plasma reactor has plasma, and so spheres don't stay spherical for long. So they're less perfect than you get in some other processes. But this is as it was real-time captured back in, I think, June 2017. So that's actually the date. And you can see there's a hollow sphere here. These are the crenellations. They're not so perfect, but here is the silicon dioxide blob up here. Okay, and I think we look at the analysis here. And we can go over here. So this is the, okay. So here we got magnesium, aluminium, silicon, iron over here. Titanium is carbon CO2 fused. Sulfur is 2 oxygens together. So the usual suspects here. Of course, some of these elements were in the charcoal or the graphite powder, and some of them, the silicon dioxide, was already in the fused quartz reaction chamber. But here we go. You could argue that potassium is also in, if there was charcoal used, it's in the wood, magnesium maybe. But you can see carbon, oxygen and iron, they are the big elemental compositions here. And it's FeO2 kind of ratio. Of course, you don't see the hydrogen here. And then here you can see at this point here, silicon. So the blob, the shiny blob that was there, if I go back here, silicon here, that shiny blob. Okay. So I suspect it will be silicon rich, this particular, the shinier blobs here are the silicon rich. You can see yellow here. It's quite yellow on this one. Okay. So it's becoming really rather predictable. This is rather awesome. Now, I like Tibi because he does a lot of due diligence and looks at other potential outcomes and so forth. And so he looks at abrasion processes here in this paper here, which I had a look at. And of course, in abrasion, when you're using a grinding wheel, very intense energies, very highly localized to the grinding bits that are the hard piece that does the cutting. So high energies in there, and then you typically use a fluid for cooling that, which almost always includes water or water and some emulsifiable oil as a cutting fluid. But almost in every single case, and in fact, I'm probably safe in saying in absolutely every single case, the coolant is comprised to varying degrees of the elements carbon, hydrogen, and oxygen. Okay. So extreme hydrodynamic shear, high localized impact energies, and carbon, hydrogen, oxygen, in addition to the materials that are going on. And these are some of the structures that they found. So this is a very thin, hollow structure that kind of has this structure going on. But there are some better examples down here. And this is really starting to look like the iron-rich crenellated spheres. I would argue that this might have some contamination in it because it's not the pure color, the pure spheres that you get. This looks more like the ones that you got on the inside, sorry, the outside of the inside of the thunderstorm generator, where it was tearing the metals out of the steel. On the inside of the outside, you got the more pure, smooth, globular, dendritic structures on the spheres, where it's almost exclusively, if not exclusively, iron and oxygen. So here you have the cutting grain, and you have one of these spheres apparently formed on the boundary of the cutting grain. Moreover, in some holes in the cutting grain, there are some spherical objects as well. Okay. So again, here, some of these structures. And note, it looks like we've got a pole on this one as well. The classic one pole on one side of the structure. Okay. This looks like it might be hollow on one side, but it might just be the shadowing. Single near spherical melted chip, that's what they're calling it. And so on. And there's a whole cluster here. Here, blah, 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 on the cutting chip here. Okay, so on the cutting face of the cutting chip here, we have these structures. Single near spherical melted chip, microcrystalline sintered carbon. Oh, hold on. What is this? Corundum? Boom! The material they are using for cutting the metal is corundum. It's aluminium oxide. It's aluminium oxide. That's what they're using to cut the material. And you know what? They've got water and carbon and hydrogen-based synthetic oils in there. Long chain oils. With emulsificators and so on. They have everything necessary to produce the Lena process and aluminium in play, right on the cutting surface. Now, it's not going to interact. That aluminium oxide is not going to break down ordinarily if you keep that structure cool, if you really give it a lot of coolant. And actually in their conclusion down here, and by the way, here we've got a ball with some thing coming from it. In their conclusion, down here, blah, blah, blah. In this paper, the selected issues have been discussed regarding SEM imaging and image analysis of spherical melted chips formed on the Jawaz, blah, 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 SG abrasive grains. SG abrasive grains are carborundum grains. Carborundum? Corundrum, sorry, not carborundum. Corundrum, I'm getting my rundrums messed up now. Corundrum, it's getting late. The analysis carried out regarding spherical melted chip formation phenomena and their general morphology enabled the following detailed conclusions to be drawn. Spherical melted chips are generally represented by two morphological forms, semi and near spherical. High magnification of some spherical melted chips allows one to observe their platelet structure. The length of the plates measured from SEM micrographs was ranged from 1 microns to 3 microns. For determination of the above-mentioned forms of the chip, blah, 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 the dimensional blah, 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 spherical chips of various sizes formed as a single chip or as a cluster containing from a few to several dozen chips. The clusters analysed in this paper contain from 10 to 150 objects. The average dimension of spherical melted chips occurring singly, regardless of the kinematic variety of internal cylindrical grinding process and workpiece of material, was around 20 microns. So this is a classical size for these things to form. Anyway. Okay, spherical melted chips form generally around other types of chips. They may be localized at surface abrasive grains. So it may be localized in a surface of abrasive grains or in free interangular spaces. The carried out grinding tests revealed that melted spherical chips occur regardless of the kinematic variation. Rah, 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 rah. And then they say down here, the presence of spherical chips shows difficult conditions of the grinding process and results principally from high temperature in the contact zone between the active vertices of the abrasive grains and the machine surface. Effect of heat generated in the grinding process is particularly damaging in the case of machining of titanium alloys, which are strengthened due to blah, blah, blah. Therefore, the analysis of the number and size of the spherical chips gives the opportunity to conclude about conditions of the grinding zone in order to optimize. Basically, right. I did my homework, and it turns out that you can reduce Corundum with carbon in play at temperatures of between 1,900 and 2,200 degrees centigrade. And with hydrogen in play, you can reduce Corundum, and in both cases, this produces native aluminium. You can do that at 1,800 degrees centigrade to 2,000 degrees centigrade. So, and the process can start to occur at lower temperatures. So, essentially, almost every element, every means by which you cool has hydrogen, carbon, and oxygen in it. These hydrogen, carbon, oxygen-based things can break down at lower temperatures with the intensity of the process going on, and you can result in the formation either with carbon or with hydrogen at lower than the melting point of Corundum, and you can end up with the production of bare aluminium. Scoggy Hoggins, thank you for the £5 donation there. Bob, I think kitchen foil will have contaminations. Yes, it does. In fact, it has even small bits of iron in there. And what we found is, even with a 90-second experiment that I did in Prague with deionized water, distilled water, that around the cones of the yin-yang pairs, you start to get some of these iron particles pulled in and twisted, and they start to knot up. So at the very least, some intense magnetic force is able to rip these particles out of the aluminium into the center of this structure. Into the center of this structure. And so even just with 90 seconds, and actually Shishkin talked about how in his cavitator device, vast amounts of iron were transferred from an iron bolt into the rest of the reactor, and they changed that bolt for a non-ferrous material. And he argued that there was an intense current flowing. I argued that there's intense magnetic vortices being produced that are capturing that iron. So from my point of view, it doesn't really matter whether it is, and I've argued this in the past, it doesn't really matter whether it's concentrating the iron or it's synthesizing the iron. The point is, there is this intense magnetic field at the center of the topological magnetic monopole. And it's more interesting when you get these spherical structures forming that are hollow and other elements are going in and the process is resonant, and that is synthesizing other elements that when the whole music is ended, they are spewing these out. This experiment that this paper here is showing that with Corundum, you can end up, when you potentially don't have enough coolant there, you can have the synthesis of similar iron-rich crenellated spheres. This might partly explain the observation of iron-rich crenellated spheres in the planed steel knife inside the aluminium block. You have aluminium, you have steel, and you have possibly corundum, not carborundum, I'll get it right in a minute, corundum, aluminium oxide grains, SG grains in there. So it's sol gel. They're produced in the sol gel process. They call them SG abrasives. Okay, so yes, there's going to be contamination everywhere. So that's why it's more interesting when you have elements that can't be fluidized, appearing as if they came out of a fluid from the pole, from only one pole, in a volume that's bigger than inside of the sphere from which they're emerging. And that is why I shared a whole bunch of data that shows these more interesting processes going on. Where I'm interested in what Tibi, I think, has achieved here is he's potentially shown a very, very simple way of doing the very most basic part of the process. So this can be explored and investigated further for validity and or otherwise. And what we're trying to do in this process is to give people an on-ramp where they can see that something anomalous is occurring and that maybe that inspires them to move forward. So if they're not willing to spend $35 on an ultrasonic cleaner, maybe they've got some scrap capacitors, scrap PP3 batteries, and some access to some deionized water around the house, because there are a very large number of people around the world at universities and in institutions and at companies that do have access to an SEM, that do have access to a quadrupole mass spectrometer. And the interesting thing is, if it's mostly aluminium and aluminium fusing, and you're not getting the exchange reactions producing the silicon and the magnesium first, and then those doing reactions, then if it's mostly aluminium and aluminium, it will be producing a predominance of iron 54. And if that is the case, then if you have access to a quadrupole mass spectrometer, then you can collect these iron-rich crenellated spheres and put them into a quadrupole mass spectrometer. Thank you, Matthew Reynolds, for that £5 donation. Very kind of you. You can put these collected, simply produced iron-rich crenellated spheres into a quadrupole mass spectrometer. And if you see a non-naturally isotopic ratio of the iron in there, then you could argue that a proportion of that may have been synthesized in a nuclear fusion reaction from the aluminium. So that was the interesting thing about George Osler steel. George Osler steel was meant to be harder and didn't rust. And it might be the case that it was more of one isotope than normal steel. And when you have a single isotope, you have a much regular crystal lattice of your metal, which means you have much less attack points for corrosion. So that kind of thing might be going on. And so I'm suggesting now that with what Tibi has done, and thank you very, very much for Tibi's work in this. Thank you for having the courage to go and get those things analyzed with the SEM, because this gives many people around the world the opportunity of having an on-ramp to this process. I can't say, I don't know whether the iron-rich crenellated spheres produced in this process that Tibi has developed will have this non-naturally occurring isotope ratio. But if it does, it's going to completely change the game in terms of what people are saying about whether this is possible and what is actually going on. It's a huge potential win for someone out there that has access to this equipment. All you have to do is have access to that equipment and care enough to try, because there's zero, like, you have to be ridiculously unable to do almost anything, right? To be able to not replicate this experiment. Having said that, you are going to be producing pulsed electromagnetic discharges. And as we saw from the work of Shishkin, there is a risk that that can explode charge clusters, low and medium naturally occurring energy solitons, naturally occurring evos, chi that is in and through your body and around your body, such that it can produce up to 10 kilo electron volt beta particles, which can do radiation, ordinary ionizing radiation level damage in your body. So I'm not saying everyone should do this. And if you are going to do this, I would prefer that you find some way to do remote detonation. Okay? Keep your distance. And then secondly, it does do explosions. It does things get thrown up, and there could be hot particles in there. There could be, things you don't want going in your eyes. So people, you've got to have protection. You've got to have eyeglasses, and just safety, safety, safety. That is the absolute key thing here. Okay, so I'm going to answer any questions if people have them. But the long and the short of it is, Anatoly Klimov, the man in Russia probably most likely to know more than anyone else, and the initiator of the NetIQ and the N-Gate plasma vortex reactors. They are based on a subset of his technology. Thank you very much, P. Atlantis, for that donation. Thank you very much. He is saying, and has shown over many years, that he produces transmutation in a plasma vortex reactor. He is saying very specifically that aluminium and water in the Alice propellant is likely to produce energy production that is between 4 and 10 times that by weight of TNT. This is not nuclear explosion levels, but it is non-chemical, it's exceeding chemical reactions to the tune of 2 to 4 times. Okay? And it does have implications in dual use. It's already being done in dual use, and it's already public what they are doing. Okay? But they're not admitting that the extra energy potentially is coming from low energy nuclear reactions, from the magnetohydrodynamic fractal toroidal geometry producing structures that can cause potentially the fusion of aluminium and or parts of water into iron and or other elements. But I'm saying that given that what we know and what we have done, that may be a possibility, and we now have a no excuse on-ramp for people investigating this field. So I'm going to look at your questions now. So Rickard Berenson says, so how would you argue is the most effective way to scale this to create elements in abundance to replace mining of rare metals? If your element is really rare, then two methods have been shown to do this. The SV-Adamenko method, which is an electrical discharge, very similar. I mean, what you are looking at here with what Tibi has done, if you're going back to my ICCF 25 presentation, I wanted to understand what wire electrodischarge machining was doing, because it hasn't ever really been explained. Essentially, you have a dielectric barrier in there in the form of water. Now, some people argue that water is a fluid and it's not like the aluminium oxide that was being used by SV-Adamenko as his dielectric barrier, which was a solid. But and also Ken Shoulders used a dielectric barrier to produce his EVOs. Okay, but water is the dielectric used. It is the barrier between the cathode and the anode. The cathode is typically the wire that is charged, and you mustn't produce an arc. It does not produce an arc. It produces something, and it definitely produces a cavitation bubble. And in that high energy process, it's of high enough energy to produce HHO. So HHO is in there. Cavitation bubbles are in there. Cavitation bubbles collapse in this toroidal structure, and the toroidal structure will be compressing and whatever, and there's plasma and stuff in there. When I looked at a sample that had gone through this process, in 90 seconds, I found a structure on the cutting wire that looked almost exactly like the magnetohydrodynamic structure that does the work. It had a sphere of the cutting material, and then next to that it had a sphere of carbon, and then it had an S shape in the standard magnetohydrodynamic structure with carbon over on one side. I'm pretty certain that the same process is going on. And what's happening is it's producing a spherical boundary layer of an exotic vacuum object where the boundary layer is of a higher binding energy than all ordinary atoms, and that causes the metal which is being cut to disintegrate. The belief is that the discharge hitting the metal is vaporizing the metal. That's the belief of what is going on. But they say it's a discharge, but then there's no arc. So if it's a discrete spark which is then cut off before it produces an arc, then that produces an exotic vacuum object, which is an electron cluster, which have ions to stabilize it. So whichever way you're looking at it, it's very similar to the process that we're talking about, this plasmatoids, plasmoids, and so forth. And so wire electrodischarge machining is a tool that you can go out and explore this phenomenon with. I've argued that the extreme hydrodynamic shear with HHO cutting torches, that's doing exactly the same thing. Again, in both cases, you typically have hydrogen in play, and often it's water in play. Obviously, with HHO it is. In the case of this cutting, you've got water in play, definitely hydrogen in play. And then, so essentially what he's doing in this foil process, so if I go and bring up what we were looking at earlier here, and we put it back in the background here, what he's doing in this foil process is he has the dielectric barrier of the deionized water in between the two aluminium plates here, and is essentially doing wire electrode discharge machining, in my opinion. And you are seeing, and what you see on the cutting tool of the wire electrode discharge machining is these scalloped spherical, partial spherical sections cut out of the wire, which is exactly what you see in the hemispherical section cut out of copper in the Henk urine structure. So it's a combination of something similar to SV Adamenko, something similar to the wire electrode discharge machining, or even electrode discharge machining, something similar to that, and something similar to the Ultra experiment. A lot of those things are being brought together in here, and in many respects, it's very similar to these discrete discharges that were done by Dr. Matsumoto in the early to mid 1990s. In his case, it was a single wire into water with the pulse discharge, and this is effectively the aluminium is providing the single wire. So, and you'll hear me discuss this with Tibi on the call. There was a research group, if this really is this unique iron oxide state, which can normally only be produced by using like 270 gigapascals of pressure in a diamond anvil at 1700 degrees centigrade, if that is what is being created, or similar conditions inside the magnetic compression in the core of these toroidal geometry structures, if that's really what's going on and it's producing this FeO2, then the US Department of Energy looked to study if this FeO2 could cause, through electron scavenging, the dissociation of water with ordinary solar photons. So here's the thing. It is a potential opportunity here to create in bulk these iron-rich crenellated spheres using this process of Tibi, and put those into a little petri dish with deionized water and put that outside and see if you produce hydrogen in normal sunlight. If that is the case, we have a solid state potential way of producing hydrogen and oxygen from air. Sorry, from normal sunlight. That is phenomenal. It's direct production of a fuel from sunlight. Okay, so P Atlantis, does it always produce 3 areas of pitting? No, this is just the one that he showed. Sometimes it's 1, sometimes it's 2, sometimes it's 3, and it's random where it goes. But you know what? Knock yourself out. Don't actually knock yourself out. Don't knock yourself out at all. I mean, it's a phrase, like break a leg when you're going on stage. None of those things. Just have a go and see what you see. Where can I form more information? Blah, blah, blah. So is there a material that can shield the radiation? Hilariously, it's aluminium foil. Thin layers of it. And if you go to the MFMP YouTube, I produce a shield that I believe would be capable of doing this. There is also the shielding technology developed by Alexander Shishkin and his colleagues to shield from the radiation that comes from this, which uses the same material, silver activated zinc sulfide that was used in Crookes tubes that Tesla used for his shadowgraph experiments in the 1800s. And so I believe that this is the... Oh, I really think I'm seeing iron-rich crenellated spheres in the center of here. I'm totally keen to find out whether that's the case, and it might well be. It might well turn out to be. But we'll see. Yeah, so I will include links to both of those technologies. I show how to make a shield, and I would only operate... I mean, you can do what you like. That's your choice. But I would operate behind a shield. In fact, I've got the shield next door. I can go and grab it. Here is my shield. So I've got a 1 each piece of polystyrene here, and it's cellophane, which is obviously made of cellulose, and cellulose has been known in films to stop this strange radiation in its tracks, and also the aluminium kitchen foil. And there's 7 layers of that, so there's many different changes of impedance on there. And then I've got a tag down the bottom which is connected to all the metal parts, so I can either there you go, I can either bias this negatively or I can put it to ground. Yeah, so P. Atlantis says probably forms pitting in the areas where the top layer of the foil is closest to the bottom layer. Almost certainly, yes. And that moves once it's happened once. The thing is that the reason he's curving it up at the edges, right, that he curves it up, so like you put the water on there, but the piece of aluminium foil that you put on top, it needs to have the edges curled up so that you don't get any charge concentration and sparking. So he's got these curled up, yeah? You want it really ideally curled up on all 3 sides. 4 sides. 4 sides of a square, right? Bob, was there any analysis of the water drops residue after sparking? No, and he's only been looking for the iron-rich crenellated spheres, but because they can be separated. But if you had access to SEM, obviously you would want to try and look at whatever else is there as well. And so there's a big blue ocean of opportunity for people here. You know, this is so ridiculously simple. If you've got access to equipment, you're already onto a winner. And you've got a small window of about a week or 2 before Alan Goldwater has a go at this, because he's working on other things at the moment and he can't get to it. what he said in his description. I'll include the basic description that he gives. I love the fact that these look semi-regular to me. These really do look like they're spatially quite regular. Yeah, even the shield is cheap. This is absurdly. I mean, this is an experiment that should, if it turns out, if this turns out to be the lab rat that it looks like, because it's merging so many concepts that we have shown and observations that we've shown over the years into one simple experiment. If it, there's no reason why this. If it shows the process and the process is verified in the fullness of time to be true, it could be the introductory experiment. It's the experiment 101 you do to get into understanding what you're doing here in secondary school. Oh, Ken, that's very upsetting. But I do know that that Paul Harris has a gas chromatograph, so he could be able to analyze the water to see if there's been any changes in there. So we do have that access. I mean, obviously we have a gas mass spectrometer as well. Yeah, if we were here in 1990, where we would be now? Yeah, well. Don't underestimate their ability to try and shut things down. But yeah, this is a thing of great beauty that we are seeing these kind of structures formed. Whether the iron is being extracted and the silicon is being extracted from contamination in the aluminium, this is something, I did actually buy 10 sheets of 10 by 10 centimeter 5/9 aluminium foil, but it never turned up, and yeah, that was disappointing. Yeah, Rickard Berenson is saying anyone who's physics, chemistry, electrical engineering student should present this experiment for their professors and demand answers. Yeah, not just that, if typically when you have an SEM session, you're testing 1 or 2 samples, right? And in the SEM table on bigger SEMs, you can put 20 samples in there. So there's nothing to stop, other than people really desperately not wanting to see this, students and professors all over the world from having a go at this, because the barrier to entry is basically 0. And chucking it on the SEM and just seeing for themselves. Just seeing, because what actually Tibi did was he scraped off the material. I would like to see the foil put into an SEM directly and to see if the iron-rich crenellated spheres are formed, partially some of them, in the center of some of these structures. That would just be awesome. If they are. I kind of suspect they would be. It would be a great high school senior science project. Yes, for sure. Do we know why? So Randy Lahi says, do we know why iron is among the produced elements? How would changing the aluminium to a different metal change the products? Iron is, maybe you missed that part, but let me just show you. Iron gets produced because it has iron 56 and nickel 62 have the highest binding energy per nucleon of all ordinary nuclei. So that is why iron actually, I think in Melvin Miles did a study, I think in 2003 or 2009, and found that the most common element produced in all Lena experiments, regardless of what elements they started with, was iron. And these are from major labs with all of the right procedures in place to make sure things are done in the right way. So let me just find the presentation that we're talking about here. So basically, in our ultra experiments that look like this, we did an exploration to confirm that it does produce hydrogen, and we did this live and showed that yes, the hydrogen gets produced after a period of time. The way that it's produced is well understood. You break off the oxide layer, and then if you're over 25 degrees, the bare aluminium reacts with the water, produces aluminium hydroxide and hydrogen. But I wanted to run this for a long period of time to see if there was any transmutation, and on one of the foils, the one foil that I looked at, there was a structure here, for instance, and it had a large hexagonal structure. You can see it in this video here. And in the center, it had this toroidal structure in the center of the hexagonal structure where it seemed to have iron, aluminium, and the exchange reaction products of aluminium, which are silicon and magnesium. And here we go, aluminium plus aluminium goes to magnesium isotopes and silicon isotopes. And when you have magnesium isotopes and silicon isotopes, you then get production of the isotopes of aluminium. Okay. So Arvid Cinematic says, I wonder if this could be tinkered to control the average distance of these spots. Would the crenellated iron-rich spheres be useful on their own for things? Yes, well, I already explained how they might allow for normal solar light separation of water. So that would be my first. I've been dying to find a way to produce these things in mass in order to do an experiment like that. And this might just be the way to do that. I don't think you need to go higher than the voltages suggested. 35 volts I think is probably fine. I don't think this is necessarily one of these experiments where it gets better as you give it more power. So ZBK Wahoo says, we'll let you know how it goes. Great. Liam Weaver says, iron is the most stable nucleus. Everything falls towards it. That is the idea, but with transmutation. So the question earlier was, how can you make elements that are heavier than iron or elements that are rare? In the work, the cavitation work, where, by the way, in the cavitation work of Griggs, he had an aluminium rotor, looked like there was transmutation going on there. Go and look at the 1991 presentation he gave in MIT, on the outskirts of MIT. In the work of Nanospire with Leclerc, they had aluminium, I rest my case, aluminium perforated sheet in a rolled up into a Swiss roll. Then he had a pump from a pond system going through the aluminium foil and to a pressure drop. And they produced every element in the periodic table. That's their claim. Every element in the periodic table. And they even produced transuranics, and in that experiment that ran for about an hour, they gave themselves radiation poisoning. Now, was it normal radiation, or was it radiation from strange radiation coming out? It may have been a bit of both in their case, because they ran it too long. And this is the difference. When you have an explosive system like this, you're likely to only get iron, because it's not a resonant system. In the cavitation process, Kladov showed that the longer you leave it in his cavitator, the more elements you get. And that's because if you have a resonant place, and what you're looking at when I'm showing you this here is a resonant spot. This here is a resonant spot. And so the magic is located there, and it keeps building and it keeps building. And if we let it there long enough, maybe it would start to produce bigger and bigger elements. The point about the Ultra experiment, we deliberately used thin foil, whereas in the case of Leclerc, they used like 1 mil, 1.5 mil thick aluminium sheet that was perforated with circular holes of 2 different sizes. This is a standard type of material you can get from a DIY store. But it is highly risky, that experiment. You can give yourself a lethal dose of strange radiation in an hour, and that's talked about by Shishkin. So I would avoid that. But aluminium, again, is the case. Remember Kladov. Let me bring up Kladov. So this is how, you know, I had a hunch in 2017, in March 2017, which is 8 years ago. I presented at the IIT, the Technical University in Mumbai. I had a hunch that aluminium was the key element to rapid processes going on in Lena, and it certainly has not disappointed in the intervening time. So if we go to Kladov, the translation I did of his patent, let me pull that up here. Kladov added, wait for it, aluminosilicate 5% solution to his reactor. Aluminosilicate. Now, what am I saying? I'm saying that the iron is synthesized from aluminium alone, or aluminium and silicon principally. He added aluminosilicate to his cavitation reactor. Okay, so I'm just going to bring that up now. So the patent, the thing you're looking at on remoteview.icu is this patent translation. I reconstructed this from 3 different patent sources because none of them were adequate. And thank you to Shishkin for sourcing me the Russian patents. Method for obtaining energy, Anatoly Fedorovich Kladov. And this is from 2nd of July 1993, just after the end of the Cold War. Desperate attempt to get these things out to benefit. Unfortunately, he died 10 years later. That's the cavitation multi-stage system. Here, most of his experiments were 2 to 6. Most of them actually were in the range of 2 to 4. Same as Anatoly Klimov was saying. But by adding 5% aluminosilicate suspension, 5% aluminosilicate suspension, the COP went to 11.61. 11.61. Boom! There it is. By having aluminium and silicon, and often with these things, the aluminosilicate is like felspar. It's like potassium aluminosilicate, or it's sodium aluminosilicate. If you add sodium into the mix and you have transmutation with sodium, and sodium is all one isotope as well, and it's 23, so it's a spin isotope, so it gets pulled into the material. If I go and do that reaction right now, I'm going to do that reaction right now. We're going to go new tab here, and I'm going to go nanosoft.co.nz. Okay. I'm going to make this a little bit bigger for you guys. And we're going to do fusion reactions here. And we're going to go sodium, Na. We're going to go aluminium. And we're going to go silicon for our 3 reaction products here. Oh, and because we're in water, let's put H and O. Okay, so I'm showing you how to do this here right now. This is how you can do it with a freely available reaction calculator. Thank you, Philip Power and Dr. Alexander Parkhomov. Thank you to the people that made it possible. We do the equation here. Look at the top of the equation. This is the O17. Of all of these reactions, the most energetic is O17, O17. This is the reaction that I predicted occurred in the cavitation reactor of Binge-Wen Huang, and it produces 28.32 million electron volts. But when you get down to here, oxygen 18 and sodium 23, 25 million electron volts. Here, sodium 23 and sodium 23, that's the first naturally occurring isotope in abundance. All of sodium is 23. That produces 25 million electron volts. It's the highest single isotope element reaction of all of those elements: sodium, aluminium, silicon, hydrogen, oxygen interaction in fusion. So I believe that Kladov was using sodium aluminosilicate 5% in the water, and it yielded 11.61 COP. That is highly practical levels of energy production. To actually show you what it is, the input energy was 72 kilowatts. The output energy was 836 kilowatts, nearly a megawatt of thermal power coming out of that cavitator from 72 kilowatts in. Okay? Aluminosilicate, aluminium and silicon. Aluminium and silicon. What was I showing in my presentation? That. When you get exchange reactions of aluminium, you get magnesium and silicon produced, and after aluminium and aluminium, which is the most energetic, producing 21.84, aluminium and silicon isotopes produce the other isotopes of iron. Have we got John in the house? Yay, we got John in the house. I'm so pleased that you are out and able to look at recovery. John, it is your work that taught me that aluminium is one of the most important elements in LENR. It's one of the reasons in 2017, on March the 3rd, 2017, at IIT Mumbai, invited by Mahadevan Srinivasan, who was the lead of the replication of Pons and Fleischmann in 1989. He was the lead author in the replication of the two lead authors there in Babratomic Research Center. He invited me, and when I went there, based on my understanding of your work and the properties that are unique to aluminium. Aluminium is totally unique because of the conductive elements. It is the lightest, and it is stable in air, but it is non-diamagnetic. It's a single isotope. And so, for instance, if you take gold, silver, and copper, they are all diamagnetic. Aluminium is paramagnetic. It goes into these clusters. It's also a spin nuclei. It's 27. Now, copper is spin nuclei, 63 and 65, but it is not paramagnetic. Silver's two isotopes, both diamagnetic. The element that's most interesting beyond aluminium is tungsten, and we know tungsten vanishes. We know that from David Hudson in the 1980s. We know it from, what's his name? Mizuno in the 1990s. We know it from Sapphire Group, Orion Energy, in their Langmuir probe. We know it from Henk Uren. And we also know it from, of course, Langmuir in the 1910s. So tungsten is diamagnetic and highly conductive, and so it disappears. And so we also know it from cavitation material production with Suhas Ralkar in 2017. So, but aluminium is cheap, and it is the third most abundant element in the crust, and potentially it is, you know, there was an announcement that China has enough thorium to run its country for 60,000 years. I can guarantee you, when we crack aluminium fusion, we have enough energy just in that particular reaction process, potentially to run all of humanity for essentially forever. Excellent, John. So yes, John has confirmed that there was a bladder stone, and I hope that you can have that removed by ultrasound or what they call it. What is it? Lithoplasty or something? I don't know, something like that. People ask me what other elements should you be working with. I just don't see a reason why you shouldn't be working with aluminium. Aluminium was nearly 49% of the most bomby bomb ever detonated by the US government. Castle Bravo. And you know what? In the Alice propellants, they're using nanoclusters. Do you not think that in the detonation of that fission fusion bomb, because it has a fission trigger, the plutonium, and the overall fusion going on with the lithium deuteride and the normal uranium, not refined. This is a dry bomb, not a cryogenic bomb. Okay? When that detonates, do you not think it's going to atomize the 49% of the mass of the overall Castle Bravo bomb into itty-bitty atoms and nanoclusters of aluminium? I think it is. Do you not think they're going to be super hot and ionized? Do you not think there's going to be lots of magnetohydrodynamic shear? Do you not think that there's going to be loads of these structures capturing whatever else is going on in the dynamics and producing extra energy from the fusion to iron? I think what Avi Loeb discovered off the coast of Papua New Guinea within the fallout zone of the Castle Bravo bomb was in fact fallout, and the iron from Castle Bravo and the iron crenellated spheres that he captured, which contained uranium and two other elements that are typically in fusion and nuclear bomb testing. Why are they there? They're there because it's fallout. And the iron is there because the iron is synthesized from the aluminium, in my view. That is what I'm saying. Avi Loeb, in my view, did a huge service to understanding the future of energy. A huge service by looking for alien stuff. Oh, so great to have you here, John. I don't know if you know, but Yin, whose birthday it still is on your side of the pond, it still is even in the UK for the next 3 minutes. She was also in the chat earlier. I don't know whether she's still there. Okay, John, it's wonderful to have you here. It's just beautiful magic, and I hope we can work together. So I'm going to ask John formally here. I would like to run with Paul Harris later in the year, possibly in August. A second attempt at replication of the Hutchison effect. Of course, we had 2 computers fail, lose their battery charge, and we had 1 terabyte SSD corrupted, and we had 1 pair of pliers break in my hands almost immediately after the thing was shut down. That's what we know happened. But we would like to have another attempt. Oh, and also feeling ridiculously disgusting inside a certain sphere next to the experiment. So that was horrible. The physical feeling. But we'd like to run another experiment, probably in October. We would like to invite George Hathaway and yourself to be participants in that experiment. So if you are up for it, you need to get your visa, or passport rather, and we would love to have you as part of the experiment. That's my formal request. Okay, so just in quick summary today, this was O-Day, Conundrum. Now, the reason I made this O'Day is because of the significance of Tibi's work is in line with the overall thrust and understanding that we've developed over many, many years. O'Day Corundum Conundrum. It is aluminium oxide, which is a highly stable compound which was used in Nernst lamps because it becomes conductive over 1000 degrees C. And it is, as elements, aluminium and oxygen comprise of 54.8% of the crust. If we can make this into an energy technology, it is literally available everywhere on Earth in essentially unlimited quantities. We have a lot of history in this. The Ultra experiment and Matsumoto's wire experiment were the simplest paths to understanding this process in a way that really there's no excuse why any technical institution couldn't explore this science. And we showed that in an Ultra experiment, we both produced hydrogen as is known, but also in a typical mark of this process, it would appear that spatially arranged, there is magnesium and silicon, which are fusion fission, that is 2-to-2 reaction products of aluminium and also iron present in this area. And that once you take those aluminium elements and produce isotopes of magnesium silicon, that gives you the silicon that in combination with aluminium produces all of the isotopes of iron. Okay? And that I believe that what Anatoly Klimov, who should know, who knows that nanoparticles of metal in a system where you have extreme multi-axis hydrodynamic shear, because he has this Tesla and Ken Shoulders inspired plasma vortex reactor technology that is currently one of the leading technologies, versions of this in NetIQ, and then the people split up with NetIQ and became Engate. These are the same technologies developed from collaboration with Anatoly Klimov. He is saying that this aluminium nanoparticles and ice are producing Lena effects, and that is producing intense propellants. And we know that aluminium does not react, pure aluminium. So if you synthesized your aluminium, for instance, as nanoparticles in a argon, and then you froze that, and then you froze that into water ice, it would not react with the water ice all the time that it's as ice. When you start heating it up to room temperature, it starts to react and produce hydrogen. If you had some sort of an igniter and you went into high temperature and pressure, it would produce intense amounts of production of heat from the chemical reaction. It would produce hydrogen that could also be burnt with air. And in addition, with the intense magnetohydrodynamic shear, you could produce Lena. And he's claiming that such mixtures of nanoclusters, and he's even suggesting carbon could be a typical nanocluster. And he's done these experiments as early as 2001. So we're 24 years later discussing this. He shared a video from 2001 where in a plasma vortex reactor, they produced laser action from C2 plus ions. He actually produced lasers action within there. So that is telling you that he's able to produce mass coherent matter, or coherent light rather. And he's saying that in these systems, the typical COP values from the Lena process is 2.4. And we know it's Lena because we have chemical elements synthesized by transmutation, observed both live in optical spectroscopy, which he shared that work, and EDS spectroscopy, which he shared. And that the combination of these two, the chemical and the transmutation, leads to a energy density that is 4 to 10 times more than TNT. So I did the equations and I work out that TNT is 4.184 megajoules per kilogram, and that by weight, if you have a kilogram of the right stoichiometric mix of aluminium, water and O2 from the air, it produces 10.46 megajoules per kilogram, which is 2.5 times the TNT. And if you times the 2.5 times TNT by the estimated 2 to 4 times COP, you end up with 5 to 10. This is absolutely comparable with his claims. I believe his claims are correct. Then in the second part of the presentation, I talked about Tibi's work here. I will share the link on Lena Forum, and essentially he did some experiments and ended up with these regular arrays, and I think we got some iron-rich crenellated spheres going on in here, and he produced the classic iron-rich spheres from the low-voltage experiments. And the silicon oxide, I believe that this will be found to be true, that's what that is. And these are regular sizes, and this little one is associated with this one, and this little one is associated with this one. I don't think that's from chance. And he has this wonderful experiment which we shared, and yeah. So that was Ode Corundum Conundrum, and I want to thank the donors today. You absolutely knocked it out of the park. I want to thank particularly in order, Vanilla Isis, thank you very much. Thank you, Winona Riders. Winona Riders. Oh, that's funny. I like that handle. Thank you very much, Black Tie, Bob Wildfish. Incredible support there. Thank you very, very much. Thank you again, Winona Riders. Thank you to Scoggy Hoggins, and thank you to Matthew Reynolds, and thank you to P. Atlantis. It's very kind of you for your generous donations. My name is Bob Greenyer. I'm a volunteer with the Martin Fleischmann Memorial Project. Buenas noches. Dobranoc. Good night.